Okay, let's take a look at class example problem unit E2, page 3. Assume that the drag on a small sphere placed in a rapidly moving stream of fluid depends on the fluid density but not the fluid viscosity. Okay? Use dimensional analysis to determine how the drag is affected if the velocity of the fluid is doubled. So the question is, if you increase the velocity of the fluid to double, so twice as much velocity. So how much increase do you have on drag? Okay. So this is the case that sphere, then incoming flow. Rapidly moving. It's kind of interesting term. So what do you mean, the rapidly moving fluid? This is literally high Reynolds number. Okay? So Reynolds number in this case is pretty high. Rapidly moving stream. So this is a sphere of diameter d. Then obviously this sphere is going to experience a drag. Okay? So we do know that the drag on a sphere. This is aerodynamic drag. We are going to study a little bit more in depth about the drag on a sphere in aerodynamics 1. However, we do know drag depends on multiple things, but it depends on diameter of the sphere, velocity of the sphere, and density of the sphere. And oftentimes the drag, aerodynamic drag on a sphere depends on viscosity, usually. Okay. Now the program statement says that the drag on a small sphere placed in a rapidly moving stream of fluid does not depend on viscosity. That means high Reynolds number flow. Okay? Reynolds number, by definition, it indicates how significant your viscous effects will be in your flow field. Low Reynolds number means that, yes, viscous effects pretty much dominates your flow field. High Reynolds number really means that viscous effects are totally insignificant. So you can actually ignore the viscosity. So this is definition of implicit flow. Okay? Implicit flow really means that we can for a moment ignore the viscosity. We are going to talk about implicit flow assumption in aerodynamics. Implicit flow means we ignore that. So the drag in high Reynolds number depends, let's not use F, phi, because it's not going to be the same functional relationship. Still depends on diameter, still depends on velocity, still depends on density, but it is no longer depend on viscosity anymore. Okay? So this is a drag's functional relationship between drag and diameter, velocity, density, viscosity for low Reynolds number flows. this is the functional relationship between drag, diameter, velocity, density for high Reynolds number cases. So obviously it's not going to be the same functional relationship. That's why I'm just changing F into phi. Okay? So let's apply Buckingham pi. Buckingham pi theorem is, as you know, it's a k minus 1. So originally this one involving 1 and 2 and 3, 4 independent dimension properties, namely drag, diameter, velocity, density. K is 4. If you look at each independent variables, how many basic dimensions do you need to represent each? Drag is a force. Okay, good. This is the length. Diameter is a length. Velocity is length over time. Well, it looks like force, length, time, or mass, length, time. All three used. Okay. This makes it 1. Oh, what do you mean 1? Buckingham pi theorem says this problem can alternatively be represented by only one and only dimensionless property. That's called drag coefficient. Okay. So this is the original problem statement. Original problem statement says the drag of a high speed or high Reynolds number flow, sphere over the high Reynolds number flow. The drag depends on diameter and velocity and density. Okay? So this can alternatively be described by, well, let's combine. Okay. Let's combine drag, density, velocity squared, diameter squared. If you notice, if you combine drag, which is force, density, this is a mass over volume, this is velocity, length over time squared, this is diameter length. So if you combine those variables, units cancel out. This is a dimensionless property, this is called CD, drag coefficient. Okay? So drag coefficient CD is the only dimensionless property you need to describe the same problem. So CD, drag coefficient for high Reynolds number flow, is usually constant. Okay? So that is the conclusion. So suppose if you do a high-speed wind tunnel test, okay? So come up with certain diameter of the model of sphere, then you're going to measure drag over that high-speed test. Maybe you change the velocity and fix and row, or fix and row and change velocity, I don't know. But you're going to take a measurement of drag and then compute the drag coefficient for different variables. Then you realize, whoa, wait a minute, over the range of velocity and density and drag you measured, if you determine drag coefficient out of those data, it's all constant. Oh, okay. So if you run experiment, you're going to determine this constant. Okay. So you are going to run the experiment and determine the constant. That's if you want to move on to the experimental testing. Your purpose is to determine this constant. In other words, you need to determine CD, drag coefficient of this flow. Okay. So now let's answer the question which is given here. Let's go back to this original statement. Okay. So this one says use dimensional analysis to determine how the drag is affected if the velocity is going to be doubled. Okay. So let's understand. So in this particular case, you don't even have to tell what is this constant, because what you can tell is, suppose if I change the velocity and make it twice as fast, how much drag coefficient change happens. Okay. So from this, okay, whatever the drag divided by density velocity squared d squared, this is the drag coefficient, which is constant, because this is the only one dimensionless property you can use to describe the same problem. So drag is whatever the constant you have, CD. We don't know what the CD is. You can determine CD by running experiments. Okay? But the CD times that, density, velocity squared, diameter squared. If you multiply whatever the constant you determine, which is called drag coefficient, multiply by density, velocity squared, diameter squared, you can determine the drag itself. Suppose if B is 2 times B, you're going to make a twice as fast speed. What happens to drag? You can tell that. Well, if B is 2B, this is going to be 4 times drag. Right? Because square term comes in. So here's your conclusion. If velocity is doubled, the drag will increase, not to twice as much, but 4 times. You can quickly answer the question by looking at this relationship. Now, if you conduct the experiment, you can of course determine this drag coefficient, which is constant value, for high Reynolds number. Okay. So this is a very simple example, but let's understand the fundamentals of model and prototype. Let's stop here.